Okay, good afternoon, class. I'm looking to continue our lecture from last time, talking about the MOS structure, but this time we're looking at it under bias. To remember what we did last time is we put together the metal, the oxide, and the semiconductor, and what we assumed is that the metal depletes the semiconductor, and that resulted in a depletion region. Now we're going to change the bias of the device, and that's what's going to be different from a p-n junction. And from the Schottky diodes that we work with in the past, we're going to see some new regimes that will be the focus of this lecture. Some questions that we're looking to answer are: what happens if we apply voltage to the metal with respect to the semiconductor in a metal-oxide semiconductor structure? And let's just get into it. Okay, so as before, we had for our metal semiconductor structure, or metal-oxide semiconductor structure, we have some phi bi, some built-in potential that's equal to the difference in the work functions between the metal and the semiconductor. And with the bias, the built-in potential, the new effective built-in potential will now be phi bi plus V, as shown right here. Okay, and overall, this dipole of charge, the reason why we're calling it a dipole of charge is because there's charge on the metal, there's charge on the semiconductor, and they're equal and opposite. Why are they equal and opposite? Because everything, before we joined the structure together, everything came in charge neutral. So all charge did was rearrange itself into what we call a charge dipole, just a separation of charge. Okay, and at all times, the fundamental electrostatics must be fulfilled. So what this equation is saying here in red is it's saying that the total potential drop across the structure, which is equal to phi bi plus V, is just equal to the potential drop phi s across the semiconductor, and this minus qs over cox, that's just saying that's exactly equal to the potential drop across the oxide. So it's just saying the total potential drop across the structure equals the potential drop across the semiconductor plus the potential drop across the oxide. The potential drop across the oxide is equal to negative QS over Cox. Okay. Now, the insulator prevents current from flowing. Okay, so the semiconductor remains in quasi-equilibrium. There's no carrier injection, so charge does move, but we're not injecting excess carriers, and so we only have one Fermi level in the MOS structure at this point. And so EFE, EFH are just equal to EF, the Fermi level. Okay, so these are the different regimes. So what we started with is right here in the middle. Okay, at V equals 0, this is our zero bias condition. And so what's shown here on the left is the metal. The dotted area is the oxide. The dots just are to indicate oxide. It's not indicating charge. And then the negative here in the semiconductor is representing the depletion charge in the semiconductor. Now what's going on? Well, what we assumed is that zero bias, that the metal depletes the semiconductor, and so we've assumed a p-type semiconductor. So when we deplete the holes from the semiconductor, we leave behind just the negative acceptor charge in this p-type semiconductor, and it's depleted to some distance. Okay. Now, as we apply a more positive bias, so positive bias is going down. As we apply a more positive bias, see V is greater than 0, we start to deplete more and more holes from the semiconductor. Okay, so our depletion region increases. Why is that? Well, as we apply a positive bias, if we go back to our previous slide, as we apply a positive bias, V, our total potential, effective built-in potential, becomes larger. And so how do we drop a larger potential? Well, we increase the depletion width in the semiconductor. That increases phi s, and that also increases phi ox. Now, what's special about the MOS structure as compared to the p-n and Schottky structures of the past is that if we keep going to a positive bias, we keep bending the bands down in the semiconductor. But at some point, we've bent the bands down, we've depleted the p-type semiconductor such that, remember, when we deplete the semiconductor, the energy bands are bending. Okay? And we've depleted it such that the bands near the surface of the semiconductor now have a significant electron contribution. And we call this point when that happens threshold. And we'll define it very carefully, but we define threshold at the point where the surface concentration, the minority carrier concentration at the surface, is equal to the bulk concentration in the semiconductor. So in this case, because the bulk semiconductor is p-type, it's when N, the number of electrons at the surface, the electron density at the surface, is equal to Na, the doping level of the semiconductor. Now, if we keep going past threshold, and that's called threshold because the device has changed, it's the threshold for which this surface charge becomes really important, this surface inversion charge. As we go to a positive bias past threshold, we get inversion. Okay, and we're going to explain these regimes. Now, if we go in the opposite regime, opposite direction, to negative biases, what we initially do is we have a smaller effective barrier across our device. We have a smaller total potential drop across our device, so we have less depletion. But at a certain point, as we go more and more negative, we reach a point called flat band. And at flat band, there's no depletion width at all. Okay? And there's no charge in the device. There's no charge on the gate, and there's no charge in the semiconductor. As we go as our voltage becomes more negative than flat band, we start to accumulate holes right at the surface. We're not depleting them, so the depletion is not, it's a different regime. It has nothing to do with depletion. We're accumulating majority carriers right at the surface, and that regime is called accumulation. Okay, so let's talk about these different regimes using our favorite plots where we do rho, the net volume charge density, E here, which represents the electric field, phi, which is the electrostatic potential, and logarithmic plots of my electron and hole concentrations, and finally my energy band diagram. So if I start off here where I'm applying a V less than 0, my effective potential drop across the device becomes smaller than at 0 bias. And so my depletion region shrinks. As V becomes greater than 0, phi bi plus V now is larger than before, and my depletion region widens. Okay? And so to go from, the 0 bias case is shown in red, and then we're showing as we go to V less than 0, we're shrinking the depletion width. As V greater than 0, we're increasing the depletion width. Now we can go directly from rho to the electric field by integrating rho. Remember dE dx, where E is the electric field, is equal to rho over epsilon. So in this case, we're just integrating from the right half. Why is that? Well, our unknown is QD. Okay, we don't know the depletion width. And so we start from the semiconductor side because that's the side that we have all of our statistics for, and we can determine charge. The charge in the, all we know is that the charge on the metal has to be equal and opposite to the charge on the semiconductor. That's represented by Qg, and we're representing it as a delta function right there at the surface of the metal. So as my depletion width becomes longer, my electric field, the point at which my electric field becomes, my electric field extends further into the semiconductor, and my surface electric field becomes higher. And remembering the different permittivities between the oxide and the semiconductor, we have a step going from the surface of the semiconductor right into the oxide. And that's just due to the permittivity differences between epsilon silicon and epsilon ox. For SiO2, the permittivity is 3.9. For silicon, it's almost exactly 3 times larger than that at 11.7. So the electric field jumps by a factor of 3 in going from silicon to SiO2. We can integrate the electric field to get the potential down here. So here's our potential. As we go to a more positive bias, the total potential drop across the semiconductor is larger. And indeed, we have a larger surface potential in the semiconductor and a larger phi ox. Phi ox is the potential drop across the oxide. Now we can go and go from phi to the energy band diagram here. And we see as there's a larger potential drop as we're going to more positive biases. Remembering positive biases on the gate is pulling the bands down. A positive bias on a terminal pulls the bands down. Why? Because this is a plot of electron potential, which is negative QV. So it's pulling the bands down, and you have a larger depletion width. Okay, so more positive bias, that's this lower curve here, this lower blue curve. You have a larger depletion width, and the bands are bending down at the surface. You can also see for the larger potential you apply, the more positive, the larger phi ox is. Phi ox is the potential drop across the semiconductor, across the oxide, and then phi s is the potential drop across the semiconductor, which can be seen as what's drawn here is this Q phi s. That's only Q phi s for this bottom curve, as drawn here. Q phi s for this red curve would be the difference between this point at the surface and this point in the bowl. So we can recycle our zero bias results just like we've done for the PN diode and Schottky diode. We just substitute in our expressions for the depletion width, the charges, and the surface potential. Instead of having phi bi, our new effective built-in potential is phi bi plus V. And you'll get the exact same results if you do the integration as we discussed in the previous slide. And this is what you get. So these are the exact same expressions before for the MOS structure at zero bias, but now now these are the more general expressions. At least in the depletion regime, we can just substitute in phi bi plus V. Okay. And so XD is the depletion width. The charge is, of course, changing because the width of the depletion width is changing. And QS just means charge on the semiconductor. And when we're in depletion, the only charge in the semiconductor is just depletion charge. And the depletion charge is negative for a p-type semiconductor, which we have here. It's just negative Q NA XD. That's just this depletion approximation that we're doing. The surface potential we solved before. It depends on XD, of course, because the larger XD is, the larger the electric field is at the surface. And when we integrate our electric field, we get a larger surface potential. Okay, so the next regime I'd like to talk about is flat band. Okay, now if I was in class, I would say, well, why do we think it's called flat band? And I would pause. And I think we can look at the picture and see why it's called flat band. It's called flat band because the bands are flat. And if the bands are flat like this, and let's particularly focus on the semiconductor part, it means there's no charge in the semiconductor. When I say charge, I mean no net charge. Of course, there's holes in the semiconductor because I can see it's p-type doped. But all of the perturbations we're doing at the gate are really only affecting the surface of the semiconductor or near the surface. Why is that? Well, in our approximations where we're solving this MOS structure, we've assumed that the semiconductor is really, really thick. Okay, you could take it to be infinitely thick. And so what that means is if I have some gate, right, and I have some metal, sure, it might perturb, the part of the semiconductor that's near it. But if I go far enough into my semiconductor, if I go deep enough, surely that perturbation at the surface should not be able to affect the what's happening deep in the bulk of the semiconductor. And so in all these plots, the far right-hand side is supposed to represent deep in the bulk of the semiconductor. And so we can see that the hole concentration hasn't changed from deep in the bulk at the back here all the way to the surface. And so when does flat band happen? Well, flat band happens when we apply some voltage, VFB, such that there's no depletion charge in the semiconductor. Well, what is VFB, right? What VFB is the voltage we have to apply. So flat band happens when the total effective potential drop across the structure is 0. Okay, so phi bi plus V, that's the total effective potential drop across the structure. It's 0. And you can see that in the picture. There's no potential drop across the semiconductor. There's no potential drop across the oxide. So the total potential drop has to equal 0 in flat band. At what V does that happen? And we call that the flat band voltage. The V at which that happens is when V equals negative phi bi. And we call that V VFB, V flat band voltage. And that's the definition of it. Okay? And so flat band's unique because there's just no semiconductor charge. We've basically undone the built-in potential of the metal such that it no longer depletes the semiconductor. And I should point out that if there's 0 charge in the semiconductor, then there's 0 electric field at the surface of the semiconductor, which means there's 0 electric field in the oxide, and it means my surface potential is also 0. Okay? The next regime I'd like to talk about is accumulation. Okay, so in the accumulation regime, we're going below flat band. So imagine we're at flat band and now we go even negative. So we know we don't, at flat band, we no longer have a depletion region. But now we put up more negative potential on the gate. Well, what is the negative potential on the gate going to do? Negative potential is going to attract positive charges in the semiconductor. Attract positive charges to the surface of the semiconductor. And that's what's drawn here in our picture of rho, the net volume charge density. In this case, the red line is not representing V equals 0. The red line is representing V equals flat band, the flat band voltage, VFB. So we start to accumulate this sheet of charge, and this sheet of charge is not the same as a depletion region. Why? Because in depletion region, we were depleting our holes. We were if you'd like to think of it as removing them from the surface of the device. They weren't just disappearing; they were moving over to the gate. But that's effectively what we were doing. Now we've done the opposite. We're bending the bands. If before we were bending the bands down, now we're bending the bands up. And what we get is we get a sheet of hole charge right at the surface. Now, why doesn't this look the same as a depletion region? Well, the reason it doesn't look the same as a depletion region is because if my potential is going negative, well, I keep reducing my hole density, right? So my hole density goes exponential of negative negative Q over KT. Let me see if I can write that. Okay, so let's see if I can do this. Okay, so the hole density is proportional to the exponential of negative q phi over kt. Okay. In this case, if I show you back in the depletion regime, phi is positive. You can see down in this picture, in depletion, our phi is becoming positive. What does that mean? Oops, I lost my equation. It means we're exponentially reducing the number of holes at the surface. But if once I've reduced my hole concentration by, let's say, 10x, what type of voltage drop would I have to have? A 60 millivolt voltage drop to have a 10x reduction in my hole density. Well, if I change my potential by another 60 millivolts from that, I've gone from 1/10 the amount of charge to 1/100th the amount of charge. If I do it at 60 millivolts again, 1/1000th the amount of charge. Basically, I've depleted all my holes at that point. So my phi can keep going more and more positive, but I can't deplete any more holes. Whereas in accumulation, I'm not depleting holes. I'm accumulating holes. And so as my potential increases at the surface, it does matter, if I have 10 times as many holes or 100 times as many holes or 1,000 times as many holes, that charge is present at the surface, and that exists in a very narrow region right at the surface, which we'll find out soon is the Debye length. Okay, so let's just talk through these plots. So we get a hole-rich, you can think of this as a sheet of hole charge right at the surface. We integrate this to get the electric field. And once again, we have a step in the electric field due to the different permittivities of the semiconductor and the oxide. We can integrate the electric field to get the potential, the total potential drop across the structure. And we can also plot the log of my electron and hole concentrations. And by bending the bands up, we have fewer electrons, but we basically had no electrons to begin with. If Na was 10 to the 17, then in silicon, N would be 10 to the third. And so that's just so small compared to P. And so this is what the energy bands look like. Okay, so we're starting to bend the bands up. And the key thing to remember is the accumulation region exists right near the surface, the MOS surface. Okay, and we make a sheet charge approximation that the accumulation layer of holes is very thin. It's on the order of the Debye length. And if we have a sheet of charge, we have very, very little potential drop in the semiconductor, right? If all of our carriers in the semiconductor, if we make an approximation that it's all right near the surface, then we won't have much potential drop across the semiconductor. Of course, we have to have some potential drop across the semiconductor because the bands have to bend down. But to solve this analytically, we say, well, let's just assume the potential drop across the semiconductor, phi s, is small. Let's just assume it's small. What does that mean? That means all the, phi bi plus v has to equal phi s plus phi ox. This term right here is phi ox. We've taken phi s to be small, so almost all of our potential drops across the oxide. And here we have where this QA just stands for accumulation charge. It's just the charge, it's the number of holes at the surface that are that are greater than there was in equilibrium. And so how much more charge do we have how much accumulation charge do we have at the surface? Well, if we assume that the whole charge is very thin, we have two sheets. We have a sheet on the gate and we have a sheet of charge on the semiconductor. Well, that just looks like a parallel plate capacitor. Now, what's the charge for a parallel plate capacitor? It's just QA. That charge is equal to Cox times delta V. And the effective V across this is VFB minus V. Now, why is it VFB minus V? Well, we know that when V equals VFB, there's zero charge. Why is that? Because we're at flat band. And so as we go to a more negative bias, we increase the number of holes at the surface. Okay. The next region I want to talk about is the threshold regime. Okay. Now at threshold, I said we keep depleting our semiconductor. Okay, here we are, the red curve is that V equals 0, and we go to a larger potential, increases the depletion width, and then we go to an even larger potential, and it keeps increasing the depletion width. And so you can see this in the energy band diagram right here. As I'm going to a larger and larger, more positive potential applied to the gate, I'm bending my bands down. Okay, and as I bend my bands down, I increase my depletion width. But you can see in this green case, something special has happened, right? I've bent my bands down so far that you can see I now start to have an appreciable electron concentration right at the surface. We in fact define threshold as the case when my electron concentration at the surface equals my hole concentration in the bulk. Okay, and so if we have equal density of states for the conduction band and valence band, that just means my EC minus EF is about the same as EF minus EV, assuming equal density of states. Okay, which for silicon they're very, very similar. Okay. Now when that happens, we can no longer ignore the charge, the electron charge at the surface. And this electron charge at the surface starts to become important. No, like in the blue and red cases, I do have, more electrons at the surface than I would, without effect of the gate. But that electron concentration is so small that it doesn't affect my electrostatics. That charge is just so small in the scheme of things that it doesn't change anything. But right at threshold, right around threshold, that electron charge can no longer be ignored. It becomes important. And so that's what's trying to be shown here. So we have depletion charge, and the depletion charge is negative because we're depleting holes, leaving behind negative charge. And this is showing my electron charge right at the surface, this QE. And once again, at threshold, we define threshold as the condition where the electron charge at the surface is the same as the doping concentration of the semiconductor. Okay. And now you can imagine for that blue case, the electron charge for the blue case that's kind of shown here as well. It's just so small it doesn't really do anything. Now, what we're going to see is past threshold, my depletion width doesn't change that much. Why is that? Because as I go past threshold, I mostly just modulate my charge, my electron charge at the surface, and I no longer am changing my depletion charge anymore. That's what's going on, right? Because if I move my bands down anymore, right? Let's say I'm at threshold and I bend my bands down so that EC minus EF in the semiconductor right at the surface changes by 60 millivolts or 60 millielectron volts. Well, then I'd have 10 times higher electron concentration at the surface. That's a big, big change. So it only takes a small voltage past threshold to give me a big change in charge in my semiconductor. Assuming that assuming when I say a change in voltage, I mean a change in voltage in the surface potential of the semiconductor. Of course, if I have a large oxide, then I could be dropping a lot of potential across the oxide. Okay? So we can integrate these, and if we assume a sheet charge right at the surface, it doesn't impact so what's assumed at threshold is we don't take into account the electron charge at threshold, and then we start taking into account the electron charge past threshold. Okay, so at threshold we just assume there's only depletion charge. Okay, so that's what we're looking at here. As the depletion width gets larger, the electric field becomes larger at the surface. Why is that? Well, we have more charge in the semiconductor. You can imagine your Gaussian box gives you a larger electric field at the surface. I have a larger potential drop across the semiconductor as I increase my potential across the structure. And we call the surface potential at threshold phi STH. Phi S being the surface potential and TH being at threshold. If we look at a plot of P and N, we can see that once again at threshold the electron concentration at the surface that's what threshold is defined as, is equal to the bulk concentration. Now don't let the log plot fool you. The log plot makes it look like there's a lot of electrons in the bulk of the device, but remember there's radically different scales here. This is a logarithmic scale, so the electron concentration is changing exponentially. So there's very, very few electrons once you move just a little bit away from the surface, right? Just again, if Na is 10 to the 17, then Ni squared over Na is 10 to the third for silicon. So this is only 14 orders of magnitude here. Okay, so we define threshold, right? You should keep that in mind. Threshold is when the surface concentration of electrons is equal to the carrier concentration in the bulk. And it's called threshold because it's the threshold at which the characteristics of the MOS structure change. It's changing from depletion to inversion. Why do we call it inversion? Because now we have electrons at the surface. It is inverted. It is essentially dominant N-type at the surface. It's not N-type doped, but there's a lot of electrons at the surface, or at least equal to that in the bulk. Okay? So what's the surface potential at threshold? Okay, phi ST or phi STH. Okay? Just to remind you, we're always defining in these cases the electrostatic potential in the bulk is equal to 0. That's our reference potential. And well, we know what phi has to be. Delta phi has to be across the semiconductor because we know how much our carrier concentration has changed, right? And we know that let me see if I can write here. Okay, I'll write down here in the corner. We know that the change in so N2 over N1 is, sorry about that, is equal to the exponential of Q phi 1, Q phi 2 minus phi 1 over KT. And if we take phi 1 to be in the bulk, okay, if we take N1 to be in the bulk, well, we know what it is in the bulk, and N2 to be at the, so that's what we're going to do. We're going to take N2 to be at the surface, N1 to be in the bulk. Well, we know N1 in the bulk, that's just Ni squared over Na. And we know N2 at the surface, at threshold, N2 at the surface just has to equal NA, right? So that just equals NA over NI squared, which we know what that is. If we know the doping, has to equal the exponential of Q phi 2. Phi 2 is just the surface potential at threshold. And phi 1 is just the potential in the bulk, which we've defined as 0. Okay, we take the natural log of both sides, and we get 2 natural log of NA over NI has to equal Q over KT phi ST. And that just simplifies to 2 KT over Q, natural log of NA over NI is equal to phi ST. Okay, so that's just where that's coming from. It's not that hard. 2 phi F, that's another way that you can define this band bending. Let me see if I can find a picture. So 2 phi F, here we go. So if we define, here we're, instead of looking at EF minus EV, phi F, we define that to be EI minus EF. And so how much band bending does there have to do? Well, if you know what phi F is in the bulk, and so we define phi F in the bulk, it's EI minus EF in the bulk. Remembering that EI is the intrinsic energy. When the Fermi level's at the intrinsic energy, N equals P equals Ni. Well, when does the electron concentration equal the whole when does electron concentration at the surface equal the whole concentration in the bulk? Well, it's when at the surface EF minus EI equals phi F. So let me just say that a little bit differently. In the bulk, this is what we define phi F as. Phi F we can calculate. It's just EI minus EF in the bulk. For you to have the same electron concentration at the surface, then the bands have to have bent down to where EI minus EF is equal to negative QF, phi F. And that's what that's represented here. See, EI is now Q phi F below the Fermi level. And where is this coming from? Well, just so you remember, I can write down my equations. I typically like to write down my equations for my electron and hole densities in terms of the Fermi level and band edges, but I can also very equivalently write it as, oops, let me get my pen here. I can write that N is equal to Ni times the exponential of in this case it's equal to the exponential of EF minus EI over KT, and at some point, right? And P is equal to Ni times the exponential of EI minus EF. So when is, and we're defining this quantity, we've defined that to be called Q phi F in the bulk. So this quantity in the bulk is defined to be Q phi F. So we just see that, well, when does N at the surface equal P in the bulk? Well, it's just when this quantity here is equal to negative Q phi F. Well, it's when that quantity there is equal to positive Q phi F. And for that quantity to equal positive Q phi F, that's when N and P are equal. That means the bands have to have been this way. Okay, so once we know the surface potential at threshold, we can plug it into our depletion formulas to find XD max. As I explained, the depletion width doesn't increase much past threshold, and so that's why we call it the max. It's the max depletion width. And then we can, if we know the depletion width, we can calculate the charge, the depletion charge, QD max, just substituting in for phi st into our equation for QD, our depletion charge. Okay, so we know the surface potential at threshold. What is the threshold voltage, right? Because what's the voltage we have to apply to reach threshold, right? So we know, once again, going back to our fundamental equation, the total potential drop across the structure is just equal to phi bi plus V, okay? And that has to equal phi s plus phi ox. And what we're calling is we want to know VT. VT is the voltage. We want to know the voltage. Okay, so that's the fundamental relationship. Phi bi plus V is equal to phi s, the potential drop across the semiconductor, plus phi ox, the potential drop across the oxide. And then we're solving for V such that when the semiconductor is in threshold. Well, so we rearrange this equation and we call that V VT. That's the V when the semiconductor is in threshold. So VT, we move this over to that side, right? And the voltage that we have to apply is equal to negative phi bi, because we've moved it over to this side, plus phi st, we just solved what that is, that's the semiconductor surface potential at threshold, minus QD max over C ox. That's the potential drop across the oxide. Well, we know what QD max is. That's just depletion charge, and the depletion charge just depends on phi st. Well, we can write this in terms of other parameters we know. So we can write it in terms of what is negative phi bi? Oh, well, that's just the flat band voltage. Phi st, we leave it as that. And QD max over C ox, well, QD max, that in front of QD max, okay, the expression down here, it depends on the square root of phi st, and the rest, that is just gamma. That's gamma over, gamma is equal to this prefactor, 2 epsilon s QNA divided by the square root of that, the square root of 2 epsilon s QNA divided by C ox, where C ox is out of the square root. And so we can write it this way. Now, don't let this fool you. You know, you look at this equation and you say, oh, my threshold voltage, this, oh, VFB plus this. This is a little bit alien. Sure, it's a formula, but it's not very clear where it came from. But my point to you is you can go back to the fundamental electrostatics relationship and really understand how that's here. And sure, we have some, redefinitions for some variables. You know, negative phi bi is equal to VFB. The prefactor in front of QD max divided by C ox, that's just equal to gamma. But we can express it in this way, okay? And the key dependencies to the threshold voltage is that as NA goes up, VT goes up. How do we see that? Well, as NA goes up, we can see that phi st increases, it increases, right? It's increasing logarithmically, so it's increasing slowly. And so both phi st's increase. But phi st is really just increasing logarithmically. What's increasing a lot is gamma, okay? Because remember, gamma has this Na in it. So a square root increase with Na is a lot more powerful than a logarithmic increase with Na. So most of the increase in the threshold voltage with an increase in Na is due to the increase in gamma. Okay. As X-ox goes up, Vt goes up. Why is that? Well, X-ox is affecting C-ox. As X-ox goes up, as X-ox increases, the capacitance decreases. As I have a thicker capacitance, the capacitance goes down. So this decreases. Gamma, maybe it's worthwhile to write what gamma is again so that everybody's on the same page. Okay. Okay. So as X-ox increases, C-ox decreases, increasing gamma. Okay, and you can see that in the plot here. Okay. So as X-ox increases, at a given doping, you can see that my threshold voltage increases substantially. Now that shouldn't be too surprising because imagine I had a really, really thick oxide. Well, for me to reach the same condition in the semiconductor, I have to apply more voltage. Why is that? Well, I'm applying some voltage on my semiconductor, on my gate. And that voltage has to act through the oxide, right? And I'm trying to change the surface potential of my semiconductor. Well, the thicker that oxide is, the larger the fraction of the potential that I apply on my gate is lost across the oxide versus across the semiconductor. You can imagine the opposite situation, which might be easier. Imagine I take my oxide thickness to be infinitesimally small so that it's practically zero thickness. Well, in that case, any wiggle in my gate potential, I'm wiggling my surface potential by nearly the exact same amount. Why is that? Well, because I can't have any potential drop across my oxide, because my oxide is so thin that all my potential drop is across the semiconductor. Okay. And so here's the meaning of phi f that we discussed previously, and it's the distance between the Fermi level and the intrinsic level in the bulk of the semiconductor. And all this is saying, once again, is that for you to have the same electron concentration at the surface as in the bulk, you have to have that much band bending. How much band bending do you have to have? Well, you can see pictorially it has to be the total amount of potential drop across the semiconductor has to be 2q phi f. Or the potential drop has to be 2 phi f. The total energy drop has to be 2q phi f. Okay. So we've reached threshold. And now we're going to an even more positive bias past threshold. Remembering that threshold is the threshold at which we go from depletion to inversion. Inversion just means that the surface now looks electron rich, even though it was a p-type semiconductor. It looks inverted. And so if we look here at the picture, once we're in inversion, we have a substantial electron charge at the surface. And that electron charge is going to be narrow. It's going to be a sheet charge, similar to the case that we had in accumulation, except this time in accumulation we had holes. Here we have electrons. Okay? So unlike accumulation, we also have to deal with this depletion charge. But the approximation we're going to make is that the depletion charge after threshold, it doesn't change. Okay, that's the approximation we make. So if we take this rho and we integrate it to get the electric field, we find that because we assume that the depletion charge stayed the same, our electric field, our depletion width is the same, and our electric field is nearly the same, except right at the surface. Why is that? Because we only have electrons, a significant concentration of electrons right at the surface. If we look at a plot of the electrostatic potential, as we go to a more positive bias past threshold, of course we have to have a larger potential drop across the entire structure, but we see that most of that additional potential drop occurs across the oxide and not across the semiconductor. Well, why is that? Well, because it only takes a very, very small change in the semiconductor surface potential to give me a very, very big change in my inversion concentration, to give me a very large change in charge. Okay? And here's what it looks like, right, as we go to a more positive bias past threshold. I'm getting a very large inversion charge concentration right at the surface, and because of that, I'm dropping. I have a larger total amount of charge in my semiconductor, and I drop a larger amount of my potential across the oxide. Okay. So what is the semiconductor charge and inversion? Well, we just simply add the depletion charge and the inversion charge. Okay, so the inversion charge just goes exponentially with Q phi s. Okay, why is that? Well, as we bend the bands down, the electron concentration at the surface is growing exponentially, and the depletion charge is growing as the square root of phi s. Okay, as we increase our voltage past threshold, phi s has to increase, right? If phi s doesn't change at all, then we won't have any more charge in our semiconductor. But for just imagine that phi s changes just a little bit. If phi s changes just a little bit, well, my inversion charge can change a lot, but my depletion charge is changing very, very little. And so that's why in inversion, our depletion charge really stops growing and it just becomes QD max. And we just take it to be the value at threshold. What we're going to do is, in analogy with the accumulation region, we're going to assume that the surface potential changes little past threshold. Of course the surface potential has to change. If the surface potential doesn't change, well then we can't have any more, we can't change the charge in our semiconductor. But the approximation we're making here is not that we know it has to change a little bit, but what we're saying is that the surface potential changes very, very little compared to how much the potential drop across the oxide changes. Basically, look at this picture here. In inversion, almost all of my additional potential that I apply drops across the oxide and not across the semiconductor. So that's the approximation we're changing. Why is that? Well, once again, a 60 millivolt change in the surface potential of the semiconductor in inversion is going to change my electron charge by a factor of 10. So it has a very big impact. So I only need a very small change in my surface potential to give me a lot of charge. Okay, so just to simplify our equations, we're going to make this approximation. Okay, and don't overthink it. You can't. If this is exactly true, well, it's everything I just said. But here's our fundamental electrostatic relationship. Our total potential drop across the structure has to equal our potential drop across the semiconductor. We're taking this just to be phi st using this approximation. And then this represents our potential drop across the oxide, okay? Where the potential drop across the oxide is just the total semiconductor charge, which is just Qi plus Qd max, okay, divided by Cox. Okay, so what is, we know what QD max is. What we do is we take this expression and we rearrange it. Okay, So what is phi bi? Phi bi is negative VFB, okay? And then we move phi st to this side as well. And then we just move the QD max over Cox term to this side as well. And by doing it in this way, we can just represent that as minus VT. That's the negative of the threshold voltage. That shouldn't be surprising, right? If we just cover up this QI, that's the exact expression. We said VT is equal to phi st, or VT is equal to negative phi bi plus phi st minus QD max over Cox. Okay, and so the only thing that's changed is now we have some voltage past threshold that's giving us some QI. And so that's what we see here. V minus VT is equal to QI, negative QI over Cox. Okay, which gives us this expression here, which in the approximations we made just makes it look like a parallel plate capacitor. Okay, as I change my voltage past threshold, if I double my voltage, I have twice as much. If I double my voltage past threshold, then I'd have twice as much inversion charge. Okay, and there's a negative here because my inversion charge is electrons, and electrons are negative. Okay, so that brings us to the conclusion. What we see that's special in our MOS case is that as we can go to different regimes. So we assume that we start off in depletion, and then as we apply more positive bias, we increase our depletion width until we get to this special situation called threshold, and then after threshold we get electron inversion at the surface. We can go the opposite way and go to more negative biases, and we hit flat band where we have no charge in the structure because we've basically undone the phi bi. Remember, VFB is equal to negative phi bi. So at flat band voltage, we have basically a zero electrostatic potential drop across the structure. And we have no band bending, and so we have no charge in the semiconductor. And as we go more negative past VFB, we get an accumulation region of holes right at the surface. Okay, thank you guys, and I will see you next week.